Next part of the assignment, the last piece, said, well, maybe the 10% power is not good enough. What sample size should we have used if we would have wanted to make sure that instead of only having a 11% or 89% beta risk, what if we had only wanted a 0.01 beta risk? So if we wanted to simultaneously make our alpha risk low, which it already is, but at the same time take that very high beta risk and make it very, very low, the only way to do that is to increase our sample size. So the question becomes, what sample size should we use to be able to make that work? Okay. So if I'm looking at my basic calculation here, I can say, okay, for my sample size, I'm going to need the z of the beta going in. So in this case, what is the z of the 99% beta that I'm looking to cover? So how big would my probability have to be as I go through? And I'm doing that because the formula that I need for this calculation is going to be a two-tailed test. So I need the second of these two formulas. I need to multiply sigma times the alpha z plus the beta z divided by the difference in the mu's that I'm looking at, that 5.5 minus 5.6. So I need to know what sample size, and you could do the algebra to get from the original formulas to this just by converting and solving for n as you go through. But I want to be able to plug in these two z's into the formula to get the values that I'm looking for. So the alpha that I want is going to be the 258 that I started with over here, and the beta is going to be the 233 that I get here. So if I plug that into the formula, I get a 216.28, and here's the basic formula repeated so you can see what it works. It's that 0.3 sigma times the sum of the two z's divided by the difference in the mu's, and take that entire number and square it. And since you can't have a fractional n, in order to make sure you achieve these numbers, you've got to make sure you round up to the next integer for an integer of 217. So the necessary sample size to get your alpha and beta risk down to 0.01 to get that 99% power would be to run a sample size of 217. You know that can be true because as you increase your n, you're going to be narrowing the curve. So on an n basis, this curve would be very, very skinny compared to the curve I've got here. Then likewise, this one would be very, very skinny on its different centers. So as I take a very, very skinny curve, okay, and move off by 1, notice the level of overlap is dramatically different. So if the alpha under the original curve might have been right here, okay, with everything to the right of it discounted, well, almost everything under this curve gets discounted in the same way. So as my sample size increases, I get a skinnier curve, and therefore the 0.1 difference that originally was considered very large turns out to be quite small relative to the width of the curve. And that's the calculation that we're doing. So if I run an n of 217, I get narrow enough curves that 0.1 difference in the mean becomes very, very easy to detect. And that's the basic difference we're looking at as we calculate the power of the curve.